Let's learn about one sample T hypothesis test. One sample T hypothesis test is used when you want to check what you expect is indeed what is happening. So, for example, let's say you are a company that makes pens, yeah, and you expect this pen to weigh, let's say, 10 grams, yeah, and you want to check from time to time whether it is indeed 10 grams or has there been an issue somewhere in the system where this pen now all of a sudden no longer weighs 10 grams because it's now weighing 6 grams and there is a problem. So if you want to detect if there is a problem from known expected value, you can run a test, one sample T hypothesis test. Yeah. So there are many such examples where you have a known expected outcome, and you want to test whether that is indeed what is happening. Yeah. For example, like the pen example I gave you, there could also be several such examples, like you are manufacturing chocolates and you print behind your chocolate label that says, hey, this has 100 grams of chocolate, or in this example I'm saying, hey, 15 grams of chocolate. You can print, but if customers are actually not getting those 100 grams, then there is a problem, right? And so you want to detect whether there is a problem like that. Another example being, let's say you are a drug manufacturing company, you produce drugs that help customers improve their health, and one of those drugs could be to reduce their blood sugar or maybe increase their white blood cells. There could be so many such things that you can claim, saying, hey, if you eat this medicine that we provide, it's going to increase by 20%. So you have a known expected outcome, and you can then compare whether that's actually happening. Or, for example, you have a test score in your school, you want to compare that to national average and check whether there is a big discrepancy. So many such examples that you can start to think of, like, hey, I have a known expected benchmark and I expect things to be around that, but if it's not, then I better know. Yeah. So those are some examples when you can use a one sample T hypothesis test. So we went through some really good examples of different types of examples of when we can use a one sample T hypothesis test. So let's pick one. From that, I said, hey, let's say there's a chocolate, and the chocolate is in this case weighing 15 grams, is what you have printed, and you expect that you are indeed giving your customers 15 grams of chocolate because they're paying for it. Yeah. So you do this when you want to, let's say in this case, you want to compare the sample mean, the average of the weight that you are shipping to your customers is significantly different than the known expected 15 grams? Or are you saying, hey, my hypothesis that my factory always produces 15 grams, so that's your hypothesized population mean? It's basically you're comparing your known expected value with a sample. Because what you'll do is you will not like look at every chocolate or every pen that comes out of your factory. You will just pick a random sample. When you pick a random sample, you're going to check and infer based on that random sample what's actually going on in your company. So we understand what we are trying to do here, which is one sample T hypothesis test. We know some examples that we went through as to when we can use it. And there are 3 steps. That's it. 3 steps to make a decision whether everything is actually going on as expected or not. So the first step in running a one sample T hypothesis test would be to first create a null hypothesis and an alternate hypothesis. A null hypothesis basically says, I expect the population mean, or I expect that my factory is indeed producing 15 grams of chocolate for every chocolate that I ship. So that's your null hypothesis, is status quo. I expect that it's 15 grams is my null hypothesis, meaning I expect my population mean, or I expect my factory to be actually producing 15 grams. Nothing significantly different than 15 grams. So then that's your null hypothesis, H0, or you can also call it H null. And then you have an alternate hypothesis, a different version of reality, which is like, hey, if you can prove this to be wrong, then this has to be right, which is an alternate hypothesis which says, No, population mean is significantly different from the 15 grams of chocolate that I expected. So if you can prove H0 wrong or H null wrong, then H alternative becomes true, because these are like completely opposite. If it's actually very close to 15, or it's absolutely not close to 15. There's only one of those two things that can be true. So you create null and alternate hypothesis, and you document it. You say, hey, H0 status quo population mean, or my expected outcome is 15, and that's what I expect. And if not, if I'm proven wrong, I would accept that there is a problem and that I need to do something about it. Second step, once you create the null and alternate hypothesis, you pick a sample. You go to your factory and say, hey, randomly, different days, you go and pick, let's say, 20 or 30 chocolates. In this case, let's say we pick 21 samples. Yeah. So sample size in this case would be 21. So what we do is we pick samples and we calculate a t statistic. T statistic, sample t is the t statistic for our sample. Yeah. So we calculate the sample t, which is a t statistic for our sample, using this formula, which is basically sample mean. Once I've taken the sample, I create the mean, sample mean, minus hypothesized population mean, which is what we assumed, divided by sample standard deviation, what is the variance that I observe, and sample standard deviation divided by square root of sample size. Yeah. So assume you got sample of 21 chocolates. So then your sample size is 21. Hypothesized population mean would be, in this case, as we said, 15 grams. And let's say we also, from these 21 chocolates, we actually were able to calculate the sample mean. And let's say that sample mean was 16 grams, slightly higher. Yeah. And then we were able to calculate the standard deviation. Let's say it was around 3. Yeah. So then we can calculate sample t. So if we plug all of this in, this is just a hypothetical number, you will get sample t to be somewhere around 3.5. Yeah. But you should, this is just an example that shows like, hey, from a sample you can calculate sample mean, sample standard deviation, you have your hypothesized population mean from step 1, and you can calculate sample t. That's it. These are the two big steps. Once you do that, you have a final step remaining, which is you calculate the p-value, or the probability, to find how rare is this sample, and if it is super rare, then I better take action. But if it is not rare to get this sample statistic t, then I'm not going to take action. So you calculate the p-value using standard t distribution. Yeah. So what you do is, first you calculate degrees of freedom, which is nothing but sample size minus 1, so 21 minus 1, so this will be 20 for us. Using the degrees of freedom, you can get a billion standard t values. Yeah. And say, hey, for 20, give me like t values, like a billion of them, for degrees of freedom 20. Yeah. So that you're actually getting t values very close to what your sample is representing. Yeah. So you get a billion such t values, and then you find out the probability, which is the p-value of all of those values that you got, whose all of those t values were greater than or equal to your sample t. So in a sense, you're trying to find out like, how rare is this 3.5? Yeah. So all you do is you count all of the t values from this billion sample t values that you got from sample t distribution, and you find out which of these, you count only those values which are greater than your current sample t, yeah, which is 3.5 in this case. So count all of them up, divided by, let's say in this case there was a billion, so we use the billion t values. So you get the probability value, the p-value. So let's say we get the p-value here to be around like 15, 0.15, yeah. So that's close to like, that's like 15%. Meaning, you know, this is not a rare probability. But how can you make that decision? You can make that decision based on your significance value. So step 1, create null and alternate hypothesis. Step 2, calculate your sample t. Then find out the p-value for your sample t. And let's say the p-value for our sample t was 0.15. Now we are ready to make a decision. To make a decision, we need a significance level or our threshold saying, hey, I'm not going to act if it is, not rare, meaning it has to be like only 5% probability. I need 95% confidence that I need to act, meaning this has to be rare. But what we got here, 15%. So this sample can happen much more frequently than we expect or our threshold. If 95% is our confidence or significance level, then we would want to check that the p-value is less than 5% because that's our threshold. So if p-value in this case is 0.15 is not less than 0.05, if p-value is less than 0.05, then I reject the null hypothesis. In this case it's not. So then it's greater than. So it's like we have p-value of 0.15. So what we then do is we say, hey, we accept the null hypothesis and we reject the alternate hypothesis. Yeah? So we say, hey, population mean is indeed close to 15, even when we got the sample mean to be around 16, right? So we do not need to take action. We do not need to worry. Things are going as per expectation. But the key thing to remember here is that this p-value is not significant, meaning you don't want to take action based on this sample. You may want to keep running more and more of these samples regularly to find out if you do get some deviations with a much higher sample mean, with a much higher sample t, which is indeed rare. So then you take action. So if p-value is less than 0.05, then you take action if your threshold is 95%. And meaning you reject the null hypothesis, you reject status quo, and you go to the alternate hypothesis. So now that we've calculated the p-value, which is 0.15 or 15%, let's really interpret what this means, yeah? What this means is that if we were to plot all of these billion t-values, we would get like a range of such values with 0 and let's say 5 and then let's say 10, so on, -5, -10. So if you count all of those occurrences of all of those billion t-values, some of them, some percentage of them could be like, let's say 4, and that's the height of this. What percentage of these billion t-values are 4? What percentage of them is 1? And so on and so forth. So you'll get a standard t-distribution that looks like this, yeah, a bell-shaped curve. And so then what you're trying to do is you're trying to say, hey, 0.15, right? So for my t of 3.5, which is somewhere here, there is at least 15% more, which is area under this curve, yeah? It's basically saying that, hey, this is not rare. If you start to get t-values, sample t-values somewhere here, then you only get, items right of this, right? So in this case, what we're saying is that, hey, given that this is my sample t is 3.5, and I see this area or this items that are on the right hand side of this 3.5 to be 15%, and it's much higher than my threshold of 5%, then I'm gonna, I'm not gonna take, not gonna reject the status quo. I'm gonna go with accepting. I'm not gonna reject the null hypothesis. Yeah, I'm gonna accept the null hypothesis. In this case, the null hypothesis is that population mean is indeed 15. But let's say, as I said, if you got a different sample t, instead of 3.5, let's say you got sample t that was somewhere here, and let's say it was 6. So then if you counted all of those values on the right of 6, and let's say this value was like 4%. So now if your p-value was 4%, meaning there were probability of all of those elements greater than 6, which was your new sample t, then you're like, hey, this is significant. This is because this is less than 5% threshold that I have. Yeah, and so then I need to, this is evidence against the null, or I need to reject my null hypothesis, meaning there is some problem. There is a problem. I'm no longer shipping chocolates that are 15 grams, and I need to look into it, right? So that is one sample T hypothesis test. How we can plot the sample T, how we can calculate the P, which is this area, and how we can make a decision based on this rule. P-value less than 0.05, evidence against the null, reject the null hypothesis. P-value greater than 5% or 0.05, you accept them. You continue to stay with status quo, accept the null hypothesis, and reject the alternate hypothesis. Yeah. All right, thanks.